Okay, so back with evaluation as a relation for commands, statements. The motivation is, as we discussed, that we can't define a computational version of evaluation because some commands might not terminate. Also, as I mentioned in this comment here, that if you have things like non-deterministic features, for example, so if you have a function that's evaluating, it's got to be deterministic because it's got to produce, it's a in a functional programming language with pure functions, the functions are like mathematical functions. They have to return the same answer for the same arguments every time. So non-determinism is not part of that equation. As they say, not only will it not be total, it won't actually even be a function. Right? Functions have to return the same answer for the same arguments. So we're going to use the same sort of technique as we saw with the expression evaluation relations before. We're going to define one for commands. We're going to use this notation here with the backslashes and the forward slashes to notate these, just to make it a bit easier to read. So the intended meaning is here. If you evaluate the command C in the state st, then you will end up in the state st prime. Okay, so it's sometimes commands are called state transformers because they take an incoming state and produce an outgoing state. Okay, so we'll start like we did with some of the other examples. We'll start with the definition of the rules in inference rule form, just because it's a little bit easier to see what's happening. So the simplest one is skip, right? So skip we don't need any premises for the skip evaluation. So skip relates the any state to itself, right? So this is not an axiom, this is a schema for axioms. So you can substitute in any state for st, and what it means is that every state is related to itself by the evaluation of skip, which is equivalent to the evaluating skip in any state returns exactly the same state. Assignment, so if we say we've got this assignment, x is a1, and we're starting out in state st, then we end up in an updated state where the value of x has been updated, and n is the value that it's being updated to, and the value n is defined by a val st of a1, just like in the function form. The form of this you could basically take this expression a val st a1 and write it down here instead of n. This makes it a little bit clearer. Sequencing, so if we have a C1 followed by C2 and we start in ST, then we end up in ST double prime, where ST double prime is the state we end up when we evaluate C2 starting in ST prime, and ST prime is the state that we end up in when we evaluate C1 starting in ST. So this is the chaining thing where the states sort of flow through, and the overall relation relates the starting state at the beginning of the sequence to the state we end up with after both of the commands have executed, which is ST double prime. There are two if rules, one for the case where the condition is true and one for the case where the condition is false. So in the true case, we are making an assumption that B1 evaluates to true, and in that case, the whole if evaluates to the same state that C1 does. So you can see from here, if we start in ST and evaluate C1, we end up in ST prime. And so if B1 is true, then the whole if ends up in ST prime. The false case is analogous, except instead of C1 being the thing that we're evaluating C2 here, and B1 is false in this case. And we can see from the two rules that this covers all the possibilities for if statements. Either the condition is true or the condition is false. There are no other possibilities. Okay, so the most complex one, of course, is while loops, which again, there are two rules. The simplest one is the one where the Boolean expression is false, in which case while B do anything behaves like skip. It doesn't make any difference. It doesn't make any changes to the state. If the Boolean condition is true, then we have a sequencing thing where we use the same sort of model as before that says, well, if we're going to start in ST, we need to evaluate C once in ST to get to state ST prime, and then evaluate the whole loop again, starting in ST prime to get to ST double prime, which is the final state of evaluating it. So it's important to think about what this means. So this is not defining an infinite evaluation process by a function. It's defining relations between commands, states, and other states. Okay, so you can think of it as just defining a set of triples where the first part is a command and the other two parts are statements. And this is a recursive definition of that relation, that set of triples. And that set of triples might be infinite, right? Because for infinite evaluations, the states just keep expanding, perhaps. But that's okay. So we can reason about infinite structures, but we can't reason about infinite computations in this sort of framework. Okay. Now, I'll say that slightly differently in a different way. So when we're talking about evaluation of this form, we're actually only talking about terminating evaluations, right? So just like in the expression case, we said, well, if we put division into our evaluation, what do we do in terms of dividing by zero? So the functional computational approach can't do it because there's no number that we should return when we divide something by zero. But the relational approach could do it because the relation approach is only defining the relation for the cases that work, if you like. The error cases are not part of that definition. So we didn't have to define what it meant to divide by zero. We just had to say that when we do a division by zero, it only works if the denominator is not zero. And that's similar in this case too, because this definition here is only talking about while loops that eventually terminate. Right? Because eventually you have to get to this position, this rule here with the false condition. Otherwise, the recursion here is never going to terminate. I mean, you can't define a triple for some loop where the loop is an infinite loop because you'll just keep using the same rule over and over again. You'll never get to the false rule. Okay, so that's the same as saying we don't define what it means to divide by zero. We don't define what the meaning of a loop that never terminates is, because this is only talking about terminating loops. So some people call this partial correctness because we're defining an outcome, if you like, that may not be well defined in some sense for the infinite loops. But we can also, as we'll see a bit later on in this section, we can also reason about infinite loops as well. We can say, well, there is no state where the program terminates in that state. And we'll see how to state that one in a minute. Okay, so if we take these informal inference rules, we can do the same thing that we've done with some of the earlier ones and write it down as an inductive relation, like so. Again, they're using the trick of reserving the notation at the beginning so then they can use that notation throughout the definition, and this where clause at the end specifies what it means. So the slashes just turn into a C eval. Okay, I won't go through all the detail of this because I want you to have a look at it yourself, but we'll look at a couple. So the assignment one, for example, this is the bottom of the corresponding inference rule. Okay, and this is the top. And this is valid for any state, any arithmetic expression, any number that is the value of that expression, and any variable. Let's have a look at an if one. So here's the bottom of the true if rule, and the two inputs here are the top. So there's the proof that evaluating V must be true, and the proof that C1 must evaluated in ST ends up in ST prime, then the whole thing ends up in ST prime. And the same for the other constructs as well. So I encourage you to have a good look through this on your own to just satisfy yourself that what's encoded here is the induction, so the inference rules from before. And again, it's a triple, right? It's a command and two states that we're relating in this particular case. Okay, so the problem with using a relation like this is that you have to do more work to actually prove anything, because with an evaluation function, all you have to do is call the function and a COC will evaluate it for you. But these relations are not like that. These are just essentially defining the forms of trees, like every inductive definition. And so we have to reason about the structure of those trees and how they relate to each other and things like that using proofs. So that's what this example is doing. So it's a little bit hard to read, but if you, at the top level, it's a program. Oops, sorry, it's a program and a slash and then empty state and then two slashes and then this state here. So what it's saying is that we are trying to prove that if we start running this program in the empty state, which again is the state that maps all the variables to 0, then we will end up in this state, which says that x is, everything's 0 except x is 2 and z is 4. And if we look at the program, what's it doing? It's assigning x the value 2. It's saying if x is less than or equal to 1, then make y 3, otherwise make z 4. So if x is 2, then this condition will be false, which means y won't be touched and z will be assigned 4. So this looks like it should be true, right? It's just like all the other ones that we've done in the past. This is just a theorem that we've written down. It might not actually be true, so we have to prove that it's true. So how do we do that? What you'll find in some of this material is that these goals and bits of program start to take up more space because there's quite a lot more going on than we have in the past. But now this is basically just put the goal in here. And one thing we can notice is that the top level expression, top level command here is a sequence, right? It's an assignment statement followed by an if statement. So the rule that we want to apply to sort of pull this apart is eseq, which is this, which is this sequential composition rule that we had before, where we run one command and then we run the second command with that's the output state of the first one, and that gives us the final state. So if we're going to understand what the meaning of a sequence is, we have to use that one because that's the only one that deals with sequences. Now, one problem we'll have, if I just do this, is that if we just apply the constructor, we're missing a variable because there's an intermediate state that's not mentioned in the goal. So ST is the starting one, and this one is the final one, which is ST double prime in the constructor definition, but we haven't got ST prime. Okay, so there are a few ways to do this, but the easiest way to say it is to, well, we have to give a value for this variable with a with clause, just like we have in some of our previous examples, and we have to be precise about what this state's going to be. And if we think about it, if we start in the empty state and then do an assignment of x to 2 to x, sorry, then the state we end up in is going to be the empty state with x being 2. So that's going to be this expression here. So if we do the with clause, we now have two goals, one representing the first assumption of the sequencing rule, and one representing the second assumption of the sequencing rule. Okay, and you'll see that this has been split into two pieces. So there's the x is assigned 2, and here's the if, right? And here's the initial state and the intermediate state, and here's the intermediate state. Oops, that's to work. Intermediate state and the final state. So this has decomposed the problem of proving the correctness of the whole evaluation to proving two smaller evaluations. Okay, but we do have to guess, or we do have to use our domain knowledge to know what the intermediate state should be. Okay, so if we look at the first sub-goal, so this should work fine, right? Because we designed the intermediate state so this would work, right? But basically it's if we start in the empty state and we assign 2 to x, then we end up in a state where x is 2 and everything else is still in the default position. So we can apply the assignment rule to work backwards from that. And now we just have to prove that if we evaluate the right-hand side of the expression, which is this a num2, in the empty state, we actually do get 2. And that's easy, that's just a simplification. I'll show you the, right? So the a eval can just run through that with no problem. There's no variables or anything, so it's easy. Okay, so the if case, so now we're in the if case. Now remember from before we had two rules for if. We have to choose which one of them to use because only one of them is going to be the right one to use for this proof. And we have to use again our domain knowledge, which says, well, if we're starting in a state where x is 2, then this less than or equal to will be false. Oops, I'm in trouble with my mouse again. This less than or equal to will be false. So we need to choose the version of the if rule where the Boolean condition is going to be false, which is this one. So if we apply that rule, we get two assumptions. One of them is that the two sub-goals. One is corresponding to the assumption that the Boolean condition is false, because that's the rule we chose. And the other one is the one that says, well, if it's false, then we're going to choose the else branch of the condition. And then we're going to need to be able to evaluate that in the starting state to get the final state that we're interested in. So we still have two proof obligations. The first one is easy because we can just simplify, right? So if you think, this is a lot of stuff here, but if you think about this guy, it's going to recursively traverse down into the less than or equal to and get the value of x out of the state, which is going to be 2. And then it's going to evaluate the less than or equal to 2 less than or equal to 1, and it's going to get false from that. So that's a simple reflexivity proof. Oops, I've got deleted the dot. And then the next one is, again, the thing that we're operating on here is an assignment. So we're going to use the assignment rule here. And because we chose the right state in the middle, we're going to get the right state at the end as well, right? So when we do the update, the point of the assignment is to make Z4, so we're going to get this state wrapped by another update that sets it to 4, which is what we want. Okay, and the only thing we have to finally prove is that when we do the update, we're actually updating with a value that gives us the value we expect, which is that 4 has the value 4 in the original state, which is pretty clear. Whew. Okay, so there's quite a lot going on there, but the important part is to realize that there's nothing new in the sense that this is just a tree representing a big program. We're reasoning about the starting state, what the starting state turns into after we've executed one of the statements, and then what happens after we execute the other statement, and we can prove that we get to the final state that we want. Okay, so CEval, that was CEval example 1. So CEval example 2 is the first homework one. So that's this one here. So that's a proof involving a sequence of 3 assignments, and then showing that the final state has the appropriate values of the variables. So I'll leave you to do that one. This one here, you might like to try and work on, which is to basically write a program that sums the numbers from 1 to some number x. Okay, and then I think it leaves the, and then prove that it works for x equals 2, which is what this thing is doing. One thing you'll notice about this sort of thing is that there's 2 aspects of this. One is that every time you change the value of a variable, you just put another update on the state. You don't take the old updates away. So you'll see things like this where x starts out being 2 and then y becomes 0 and then y becomes 2 and so on and so forth. Right? So you end up with this sort of stack of bindings essentially in the states. We never clean those up. So things can get a bit complicated there. Okay, so have a go at that one if you have time. Okay, so next topic is determinism. So we said before that we didn't want to use a function because we weren't going to be able to express the meaning of a while loop, for example, that may not terminate. But we still want to know that if we consider the evaluation of a command, that it's not going to sometimes do one thing and sometimes do something else. In other words, we want to know that the evaluation of commands is deterministic, right? So just because we've defined this as a relation doesn't mean that it's a deterministic operation, right? So in mathematical terms, we want to know that it's a function. It's not going to be a total function because we're not going to deal with the infinite cases, but it's going to be a partial function, right? So one way of stating that in sort of mathematical terms is if we take if we take a command and a starting state and we evaluate it and get st1 and st2, it must be the case that st1 and st2 are the same. In other words, there's not 2 different final states that we could end up in when we evaluate the same command in the same starting state. So I'm not going to go through the detail of the proof, but it's not really too hard to show that there's only one way to do everything, and mostly it sort of follows from the rules that we've defined, being each one of those individual rules is deterministic, right? There's just no way to do things in different ways. Just we can't make a choice about what to do. We really only have one choice in each situation. So that's what this guy does. But you can sort of hopefully see that we're starting to get to the power of, well, we define our semantics as this relation, and now we can satisfy ourselves that the language is deterministic, right? Just with a one-page proof or so. The last topic for today is this reasoning about imp programs. So in the following chapters, we'll do lots more reasoning about imp programs, but this just gives a sort of taste of that. So we can do things like reason about the semantics, which is what that determinism proof did before, which was, for an arbitrary command, this is the case, which is reasoning really about the language semantics, the semantics of the whole language. Whereas something like this +2 spec here, for example, is just reasoning about a particular program, which is +2. And it's saying, well, if I start out with x being some number n, and I run +2, then in the final state, st prime, x is going to be n +2. In other words, this is proving that +2, the function, written in imp language, right, does the right thing. Okay. Now I think you may have forgotten what +2 was, so let's right, so +2 is a command that just assigns x to x +2. Right, so it's not a very exciting example, but it's basically saying that the intended behavior of this assignment statement is that some value n gets turned into some value n +2 in the appropriate part of the store. Okay, now there might be other specifications you might want to have. So for example, if you assign to x, you'd kind of like it to be the case that no other variables get changed, right? So it might be that n gets incremented by 2, but all the other variables get set to -1 or something. Well, not -1, we've only got naturals. Set to 42 or something, right? So this is a partial specification because it's not saying anything about what happens to all the other variables other than x in the state. Okay, so this st prime might not be related to st at all the other positions, right? So that would be something else you'd want to prove. Let's just have a quick look at this proof. So you get to this position after you've introed everything, and you can see that what we're trying to prove is that this st prime maps x to n +2. And all we really know about st prime is that it's related to +2 and st by this assumption, h eval. So the simplest thing to do here is to invert that, and what you see is you get a mess. Basically, it's going to be saying, so let's go back again. We know what +2 is, it's an assignment statement. So it's going to, inversion is going to use the constructors of the command type to say, well, if it's an assignment statement, then I know which rule must be used to do this evaluation, right, which is the assignment evaluation rule, and that flows on to all the other pieces in the rule. So you can see in this mess that we've decided that there's a plus. So this is the right-hand side of the assignment statement, is evaluating to some number n0, and we're updating the state where x is now n0, and that's going to be st prime, and we've inlined st prime, so we've got this guy down here, and so on. One thing that is almost always useful in this case is to clear up some of this confusion, because we've got n's and a1s and st0s, and so st0 and st are the same, and so on. Get rid of those because it'll be a lot simpler. So one way to do that is just to do a subst, and it simplifies it a lot, right? Basically inlines everything. Now it may not be as obvious to you what's going on, but if you have a look at this thing down the bottom here, we're updating st at position x to the value of this thing, and then we're asking for the value of x, right? And so we had a theorem before where we said if we update a map at some position with something and then ask for the value of that thing, you get the thing you put in, right? So we're going to use that in a minute. That's this T update EQ down here. We're not going to need HEval anymore, so let's get rid of HEval, just clear it, and then do a simplification. So what's that doing? So that's taking this A-val in here and simplifying it as much as possible, because we can evaluate the 2 to 2, and we can evaluate the x to the value of x in this store here, and then the plus turns into an actual plus. So we get this, so we simplify all that down to that, right? And now when we see, well, this thing is exactly what we want, right? And we can get that because we know that if we put that into the store and then ask for it back again, we get it back again. So T update EQ will do that. Okay, so it's just a simple example of reasoning about the semantics of a particular program using these techniques. And we'll see a lot more in the coming weeks. Okay, so we're almost done. The last couple here, the next two here are the next two homeworks. In fact, the last two homeworks. So this one is x times y in z spec. So you need to go back and have a look at what x times y in z was and come up with a sensible specification along the lines of this +2 spec, right? So something that holds before, and then when you run x times y in z, what should usefully hold afterwards. So just use your imagination to come up with a useful specification. And the last question is loop never stops, which is the one that's talking about infinite loops. So loop was the program that did while true skip. So there is no, well, what we're trying to prove here is that there is no state st prime where starting in st and running a loop gets us to st prime. So this is another way of saying that the loop never actually terminates, right? And it's for every pair of states. There is no possible one. Okay, so they've started you out a little bit here, but use the hint here and do induction on the derivation that we're sort of assuming exists, and then you're going to be able to show that it can't possibly exist. Okay, so that's really where we are. There's lots more exercises as usual in this chapter. I'll make a brief mention, I think, just a little bit down here. If you've got a bit of time on your hands stuck at home, you might find this stack compiling one to be fun, because it basically talks about compiling expressions into stack machine code and then doing various reasoning about the evaluation of those programs and the meaning of the things. And I think they do optimizations and a few other things. So this is quite a nice extended exercise that they guide you through here, just to get a bit more practice. Okay, so thanks for that, and I'll talk to you next time.